Hi, I'm Mike Marin, and in this video we'll discuss the use of the partial F-test as well as how to implement the partial F-test in R. The partial F-test is used in model building and variable selection to help decide if a variable or a term can be removed from a model without making the model significantly worse. Conversely, we can think of the test as being used to help us decide if adding a variable or a term to a model makes the model significantly better. Soon, we will provide a clearer definition of exactly what we mean by better or worse. We refer to the larger model as the full model, and the model with one or more variables or terms removed from it as the reduced model. A term that often gets used here with the partial F-test is that it is used to compare nested models. Let's discuss a few examples to help explain what we mean by the term nested models, as well as a full and a reduced model. We will be working with the lung capacity data that was introduced earlier in the series of videos. I've already imported the data into R and attached it. Now let's discuss a few examples. As a first example, suppose that we have a model to estimate the mean lung capacity using age, gender, smoke, and height. We'll call this model here the full model. Now, we may want to consider something like removing height from this model. Our thought here might be that given that we know the age and the gender of these children, also knowing the height may not be necessary in our model. We can test this hypothesis. Here, we'll compare this full model to a reduced model that does not include the height variable. We would say that the reduced model is nested within the full model. That is, the terms used in the reduced model are a subset of the terms used in the full model. We'd like to know if removing height from this model results in a statistically significant increase in the sum of squared error or residual sum of squares. In other words, does removing height from this model result in increased error in our model and hence a decrease in predictive power? Conversely, we can think of this as asking the same question: does including height in the model significantly decrease the error and significantly increase the predictive power of the model? That is, does including height improve the model? This can help us decide whether or not we should include the height variable in our model. If height does not add anything to the model, we should exclude it, as the simpler or more parsimonious model is always preferable. Now let's consider one more example. In example 2, suppose that we're going to model the relationship between age and lung capacity. And we think that that relationship may be nonlinear, and we'd like to consider adding age squared to our model to allow for fitting a quadratic curve rather than a line. In this case, our full model would be a model that includes age and age squared, and the reduced model would exclude the age squared term. Again, we could say that this reduced model is nested within the full model, as the reduced model contains a subset of the terms used in the full model. We would like to know if the model that includes age squared is significantly better than the one that does not. Or again, conversely, we'd like to know if the model that excludes age squared is not significantly worse than a model that includes it. The way we will define if the full model is significantly better is by determining if the sum of squared error, or the residual sum of squares, is significantly lower in the full model as compared to the reduced model. So let's do a quick review of what the sum of squared error, or residual sum of squares, is. The sum of squared error measures how close the model's predicted y values are to the observed y values. In some sense, it can be thought of as summarizing how well our model fits the observed data. The partial F-test compares the sum of squared error of the full model and the reduced model to see if there has been a significant change in the sum of squared error, and hence a significant change in how well the model fits or predicts the observed data. Let's consider that second example, where we'll model the relationship between age and lung capacity. Suppose the scatter plot and the fit of the reduced model looked as follows. If we were to take all of these residuals or these errors, square them all, and sum them all up, this is what we'd call the sum of squared error. Now, imagine instead fitting what we're going to call the full model, a model that also includes age squared and allows for curvature. For this model, we can take a look at all of those errors, squared, and summed up. In this fictitious example, we can see that the sum of squared error of this full model looks like it's significantly less than the sum of squared error for the reduced model presented earlier. we can subjectively say that this full model appears to be better. If, on the other hand, the decrease in sum of squared error when going to this full model was not very much at all, we would conclude that adding age squared to the model does not significantly improve it and is not necessary. The partial f-test makes comparison of these two sum of squared errors, but in a more objective way, to help us decide if the decrease in sum of squared error when moving to the full model is statistically significant. The partial f-test. This test has a null hypothesis that there's no significant difference in the sum of squared error of the full and reduced model. Or in other words, we can state it as the models do not differ significantly. It has an alternative hypothesis that the full model has a significantly lower sum of squared error than the reduced model. Or stated in another way, that the full model is significantly better than the reduced model. And of course, the null and alternative hypotheses can be expressed in many different ways. Our test statistic looks as follows. We can see that it takes the difference or the change in sum of squared error from the reduced model to the full model, and this is divided by the change in the number of parameters in the model, the number of terms dropped from the model, divided by the mean squared error for the full model. We can also see, looking at this test statistic, the larger the value of the test statistic, the larger the change in sum of squared error, or the larger the difference between the two models. Let's carry out this test using R first on that example number 2. I've already prepared a script to do all of this stuff, so let's run through that. First, we're going to fit that full model that includes age and age squared. Then we can go ahead and fit the reduced model that includes only age. These are the two models that we're going to want to compare. And just for our own sake, let's take a look at the summary of the full model. We can see there that this model has an R squared of 0.6727 and a residual standard error of 1.525. If we take a look at the summary for the reduced model, we can see the R squared is 0.6719 and a residual standard error of 1.526. Just looking at these subjectively, we can see that there hasn't been very much change in the R squared or the residual standard error when we look at the full model and the reduced model. It seems that including age squared does not improve the model, but let's formally carry out the partial f-test. You can recall that this test has a null hypothesis that there is no significant difference in the models, and an alternative hypothesis that the model with age squared is significantly better. To complete this test, we can use the ANOVA command, and we'll first enter the reduced model and then the full model. In the test results, we can see the sum of squared error, which R is labeling as the residual sum of squares, for each of the models. We can also see the F statistic and the p-value for the test. Based on the p-value of 0.172, we'll fail to reject our null hypothesis and conclude that we do not have evidence to believe that the full model is significantly better. We've decided that we don't think it's necessary to include the age squared term in our model. And it's worth mentioning a reminder here that failing to reject a null hypothesis is not the same as accepting it. We have not proved the reduced model to be better. We've failed to convince ourselves that it's worse. Now let's go back to that first example and test if we can drop height from the model. First, we're going to fit the full model, and we'll call it Model 1. And this is a model that includes age, gender, smoke, and height. Now we'll fit a reduced model that includes only age, gender, and smoke, and has the height variable removed. And again, a reminder that our null hypothesis is that there is no significant difference in these models, and the alternative hypothesis is that the full model is significantly better. Again, we can use the ANOVA command, first entering our reduced model and then our full model. And taking a look at the results, we can see the p-value is extremely small. Here we will reject our null hypothesis and conclude that the model that includes height is significantly better. That is, it has a significantly lower sum of squared error or residual sum of squares. And we can see that large change in the sum of squared error when we look at the output. I'm sure you can imagine all sorts of applications for the partial f-test. The main thing here is that the two models being compared are nested. It's also worth mentioning that model building and variable selection are very large topics, and they depend largely on the goals of your model. Here we've simply presented the partial f-test as a way for comparing nested models to see if there has been a significant change in the sum of squared error. Thanks for watching this video. Make sure to subscribe to our channel and check out our other instructional videos.